So we're now starting to move to our challenges. Talks from our users on the challenges they see in their verification. Martin spoke last year actually, but at that time he was with Lentic, and now Martin is with Infineon, with a different set of challenges to those he had last year. So Martin is now Principal Engineer in Functional Verification at Infineon Technologies in Munich. And he can tell us about his verification challenges. You ready to go?
Yes, no, okay. So last time I was here for a communication, for a company which was working in the communication area. Meanwhile, I changed to Infineon Automotive microcontroller, and now I have the pleasure again to talk about the 3 challenges. And it's mainly different to that from last year. On the one side, because it's a different area. On the other side, because market improved and the challenges changed. So for me, it was a new experience. So in the communication area, the main thing was a chip has to work as specified, and you can tell it if it's working as specified. Basically, nobody asked if there was verification or something like that. It would be also okay to have a bug-free design and just sell it. Now, for automotive industrial things, is different. So certainly, it was also recommended to do verification, to do a good documentation and so on, but this was not required. For automotive, now it's different because we have some standards. We have also to show that we did the best that we can, or what is required by the market to fulfill this functional correctness. And I'm not aware, who of you is already aware of the standard? It's the ISO 26262, which is now not coming up. It's already there for a while, but it has to be fulfilled for the latest chips. And that was, I would say, for our department, this is currently the biggest challenge to fulfill this standard, because there are some new things to be done, or some things to be done much better. From technical point of view, now we have the challenge. There are some different levels. It's called the ASIL levels. It's Automotive Safety Integrity level. It's rated from A to D. A is not very strict. D is very strict. Here you have to really fulfill a lot of things that you get the certificate. One thing is, which is now coming in, for communication chips, if let's say some alpha race is switching some register and so on, basically it doesn't matter. The worst case was system crash, reboot, start the call, for example, for mobiles again, or do the internet connection again. Certainly it's much different if you drive a car and the system is crashing. So here we have to prevent it. And for that, the standard requires, for example, if such kind of a failure happens, so it should not be called bug insertion or failure insertion. If such kind of a failure happens in a critical part of the chip, there must be the chip or the system must be able to get this failure and to go to a safe state. And you could imagine this is very challenging, because digital failure normally requires a fully annotated, back annotated gate level simulation, and everybody knows for normal sized, already a normal sized SoC, it's not possible to do a full gate level, back annotated gate level annotation for every kind of such of a failure. And therefore some new methodologies has to be developed, also together with the EDA companies, and how to bring it down to a, let's say, manageable level. Additionally, some fail-safe functionality has to be implemented and verified. This is more or less a normal standard. On the other side, what we have to improve is the verification flow itself. That means, for example, checking for traceability. So you have always to document in a traceable way, in a trackable way, what you have done, that finally, if really something happens, you can show that you have really did what you could to prevent this kind of failure. And the third thing, what we have to modify in our flow, up to now, at least what I know in all of my verification history, typical way was there was some requirements specified. Long ago it was not specified, but meanwhile it's standard. Based on these requirements, we got the specification, and based on this specification, we did our verification. But this now has changed for the standard. Now the verification is not done against the specification, but against the requirements, which are basically, first of all, very high level specified, and then finally somehow pushed down up to the design. And here the important thing is also it has to, the complete development flow has to be changed, it has to be adapted to this methodology. So basically the things are not so much also technical, but also many things has to be changed in the complete development. Then the next challenge that I'm facing is also not so much technical. So in the past it was standard, or at least some years ago, in my opinion, good idea came up to have separate verification teams which are verifying, so that not the designer verify their designs by themselves, but to have separate teams. And it was, I would say, very common to have these teams not at the same site, but for example, somewhere in Asia, China, Bangalore, somewhere else. Same was done in my department. Then for some strategic reason, it changed from one site in Asia to another one, and now finally it changed again. And especially when it was at the previous site, it was very much common to have several contractors to get all this work done, and especially also many contractors which only work for short time, let's say 3 to 6 months. And now it turned out it was really not good for quality and also not for the platform-based design, because basically our chips are very much platform-based. It means we develop a module and increase it only a little bit to the next platform, add some features and so on. Here we need very much reusability, and especially so this is not, I would say, not so much related to the site, but more related to the kind of short-term contracts, and that the verification is done on different sites than the implementation. You have to ramp up this verification engineers, they do something and then they leave, so the know-how is lost. And on the other side, normally it's not so easy that this verification engineer develop the environment in the same way like the rest of the department is doing, so that it's reusable on different levels and so on. So I would say here the strategy what was done before was not the most effective one in several ways. Here we have to improve. And also this is the same thing I not only face here, it's also from my common past. This shifting and the short-term contractors, in my opinion, for verification, it's not very good. And it's always interesting for me to see how many people give the complete verification packages outside and get back the verified chip. So I cannot imagine how this is a really a cheap way, in a good way. And the third one is also a topic which is not completely new. The analog, the way how analog, I did right here engineers, not verification engineers, how the analog mixed signal people are thinking, and on the analog mixed signal side, the digital people are thinking. Certainly analog designs has a certain complexity, no doubt, but they normally need some kind of a digital design to control the analog part. At least for the big systems, it is the case. You have some controllers. And so the way how I know this analog mixed signal designer, they are very proud of their design and say it's this little bit controller we also do with a mixed signal flow, and then without specification they write a little bit control flow, make some directed tests and say it's working. And here it always turns out that never gets the quality like if a digital verification designer do this control part and a verification engineer is verifying it. So here also, we need still a little bit of a mind switch that analog designer really controls on the analog part, and every digital part should be done by digital people to ensure the quality. So that's what I wanted to share with you today.
Thank you very much, Martin. Again, is there any questions for Martin? Jail. Because of people listening in.
So, yeah, J.L. Gray from Cadence. So you mentioned that something about analog designers, the verification methods are not the same as in digital. You seem to be implying, I guess, that they should improve the verification for the analog. But I guess my question is, do you actually have some numbers that show that the analog quality is actually not good? Or you just feel that the digital methodology is better?
You mean analog, the analog part, not the signal part of the analog design?
Yes, right, the analog.
Let's say it's a completely different kind of verification. So because it's not black and white like in digital. Yeah, I cannot, I would say it is good, but it could be better. So, and it's always interesting, we always have to wait on some test chips to see if the design is really working as it's expected or not. So I'm not deeply enough in the analog design to say why this is way.
Of course, so don't you, with the digital, you also have to wait for the chip really to come back to see if it works as you expect.
But normally I would say we are much more able to do a bug-free design. So if we had a really good environment and set timing analysis and all of this implementation stuff is correct, then normally we do not find a bug.
So you're saying, though, that on the analog side, you typically do find bugs. So I guess that's my question.
Let's say unintended behavior.
Thank you.
Yeah, it's not so easy in analog.
It's a politically correct term for a bug, I think. Unexpected behavior. So our experience with working with analog companies is that a lot of the bugs appear at the interface between the digital and the analog, which is typical because that's where the communication has to happen between the digital people, and it's, as always, there's a human aspect to it where the digital people and the analog people don't correctly communicate, and it's quite difficult to model the analog accurately enough for the digital simulation. So that's where we see a lot of the bugs, and quite a lot of our customers who do analog deliberately have a chip first of all to do characterization of the analog device to get it right on the second spin. So quite a lot of our analog customers deliberately go for a two-spin or one-spin policy.
One thing
to deliberately have a second spin.
Also, another thing maybe what I face is problem. It's like software and hardware engineers. It's similar with digital and analog engineers. You talk the same language, but you do not understand.
Yes, exactly. We all speak the same language, but not quite so close enough. Close enough to think we understand each other. Okay, brilliant. Thanks, Martin.